The particles making up the weak nuclear forces are perhaps one of the most stubborn in all of particle physics because they have violated one of the most fundamental and conservational laws in all of physics, which had been formed by one of the greatest physicists of the century, even Nobel Prize winners. In this video, I would like to cover one particular type of conservation law which pretty much worked out for all the fundamental forces except the weak nuclear forces. This particular law is known as the Parity Conservation Law. So, before we go on further, I would like to tell you a bit about particle physics. So, you see on your screens is the standard model of elementary physics, and this contains all the fundamental particles known to humanity, including the anti-pairs one. These particles can further be divided into two categories depending upon their quantum mechanical spin. Every particle has this quantum mechanical property of spin. The particle is actually not spinning, but it has an angular momentum which can be mathematically represented by a g or a gyromagnetic factor. Fermions are particles which make up visible matter like you, me, and everything else. These particles include quarks and leptons, and the gyromagnetic factor for their spin is in half integers, in decimals, like 1 upon 3, 2 upon 3, etc. Whereas bosons are those particles which carry forces. They include photons, which carry electromagnetic forces, the gluons for the strong nuclear forces, W and Z bosons for the weak nuclear forces. The G factor for this spin is in full integers, not in decimals, like 1, 2, 3, etc. The W bosons, which carry the weak nuclear forces, are responsible for some types of radioactive decay. For example, the beta minus and beta plus decay. They are also responsible for the decay of some types of mesons, like the kaons as well as the B mesons. Now let's go back and understand what exactly is parity symmetry and how do weak nuclear forces violate it. The principle of parity symmetry and the parity conservation law was originally brought in by a physicist named Eugene Wigner in 1927. According to this principle, every physical interaction should behave exactly the same, even if the left and the right are interchanged, or the clockwise is swapped for the anti-clockwise. In other words, every experiment should give the same result regardless of the direction. And it is this very principle which brought in the idea of the possibility of a theoretical mirror universe. The parity conservation law states that every physical interaction in the current universe should produce the same result even in the mirror universe, where the directions are interchanged. This principle was tested out on the strong nuclear forces as well as electromagnetism, and it worked completely fine. However, there hadn't been any proof over the weak interactions. Then came in a Chinese physicist named Xin Wu, who came up with her famous Wu experiment. The main aim of the Wu experiment was to check whether the weak nuclear forces obeyed to the parity symmetry. And the way she did this was by looking at the beta decay, which was in fact facilitated by the W bosons in cobalt 60 atoms. In beta decay, there is an unstable atomic nuclei where there are more number of neutrons and less number of protons. Because of this imbalance, the neutrons change into the proton and release an electron as well as an antineutrino. This way, the double bosons change the neutron to a proton by changing the identity of a down quark to an up quark, thus converting a neutron into a proton. and thus increasing the atomic number by 1 unit. The reason as to why cobalt 60 was chosen for experimentation by Wu was because cobalt 60 has something called a nuclear spin, which basically means that the nucleus has an angular momentum and it has a spin. Now, this spin of the cobalt nuclei can either be in clockwise direction or in the anti-clockwise direction. What Shin-Shang Wu wanted to know was that if the direction of the nuclear spin of the cobalt is changed, then will the direction of the motion of the decay product, which is an electron, also change? Because physicists at that time had theorized that if an electron is decayed during beta decay, then its motion should have an equal probability in all directions. But if the direction of the motion of the emitted electron during beta decay depends on the direction of the motion of the nuclear spin of the nucleus, then parity will not be conserved, as stated by Shin-Shang Wu in her own words. So, if parity was conserved within the weak nuclear forces, then the direction of the emitted electron during the beta decay should not be dependent on the direction of the nuclear spin of cobalt 60. The motion of the emitted electron should have equal probabilities in all directions, irrespective of the type of nuclear spin. The experiment monitored the Wu experiment monitored the decay of cobalt 60 atoms that were aligned in a uniform magnetic field and were cooled to near absolute zero, so that the thermal motion do not ruin the alignment in their net magnetic dipole moments. Cobalt 60 is an unstable isotope of cobalt that decays by beta decay to the stable isotope nickel 60. The cobalt in the experiment was placed in a cylindrical vacuum tube in a magnetic field so that the nuclear spin of the cobalt could have been easily changed. When the experiment was done, Wu measured the direction of the decayed electron relative to the direction of the nuclear spin of the cobalt using something called beta decay spectroscopy. In the end, she discovered that the direction of the emission of electrons completely depended upon the nuclear spin. The emission was in opposite directions for clockwise and anti-clockwise spinning nuclei, thus violating the parity conservation and the idea of a mirror universe. Later, she and her team even published their results in a lot of scientific papers, and in the beginning they were met by popular disbeliefs and opposition, but in the end their results were reconfirmed and it was proven that weak interactions actually do violate the parity conservation law as well as the parity symmetry. This experiment conducted by Wu actually tells us what exactly are directions, what exactly is left and right, clockwise and anti-clockwise, because these things can change with respect to different reference frame. My left can be someone else's right and my right can be someone else's left. Same thing is with clockwise and anti-clockwise. So the result produced is the same even when we change directions. But this is not the thing for weak nuclear forces because they behave differently in different directions. As we saw, when the nucleus was spinning clockwise, the direction of the emission of decay products was in different directions as compared to when the nucleus was spinning anti-clockwise. So that's all for now, and I hope you like this video. I hope you learned something. And the other symmetries, how the weak nuclear forces violates other symmetries, the videos for those symmetries will be coming up in the future. So I'll see you in the next video, and bye. Have a nice day. Thank you.